So I guess we can start now with the session. So yeah, that's it, no?
How do I work this?
Here, yeah. So that should be sorted. And Control L.
Hello, everyone. Thank you, Anna Maria, for this lovely memory help. So my name is Vincent Lostanlen, although that's one of the several ways you can pronounce my name. I won't be offended, of course. I'm from CNRS, and this is a paper with Brian McFee from New York University. You may know the two of us if you've used Librosa, because we are the two maintainers of Librosa. And today we're going to talk about evaluation algorithms for sound event detection. You might think that the science has settled on how to evaluate algorithms, but it hasn't. So this paper is kind of an oddball at DCASE in a sense. It's lying in a corner of various themes in the sense that there will be no machine learning, no feature extraction, no audio data, in fact, no data analysis of any kind. And we won't be comparing with state of the art, really. However, there will be some fundamental graph theory, analysis of algorithms and their complexities, and we're releasing open source software that you're willing to use. So the problem statement is something I suppose you're familiar with, and you have a prediction, you have a reference on a timeline. Each event has an onset and offset. We're working with a single class for the moment. There's nothing like unknown classes or anything like that. However, we are working in the most general setting in the sense that one event could contain another, which is not really how we like to think about audio events, but after all, an audio annotation could look like that. And the question is, what's the maximum number of predicted intervals matching a list of non-duplicate reference intervals? And this is how you get a number of true positives, and you derive false positive, false negatives, precision, recall, F-score, you name it. So first, it's important to make it correct. And it's important to understand that it's easy to get wrong. Like, there are some heuristics about how you could get this done, which will return a suboptimal number of true positives. This is a greedy version. It's very efficient. It's linear in the number of events. But it has a false positive and a false negative that are unmatched and really should not be unmatched. There is a way that in which we could pair these. So this is another greedy approach, again, two unmatched events. And this is the optimal approach, where you see that each prediction event is matched to one and only one reference event. This is done in SED-eval already, thanks to a 1973 algorithm known as Hopcroft-Karp. But there's a problem with Hopcroft-Karp, is that you need to build a graph early on. And the way you build a graph typically is by brute force. You would analyze every candidate pair and see if there is some overlap in terms of intervals. And so that has quadratic complexity in the number of events, which is n. So the brute force approach for event matching is n factorial, which is completely unscalable and out of the question. Hopcroft-Karp brings it to n square root of n. Brute force is quadratic, and our algorithm brings it to n log n by sorting lists. And I will insist on the fact that trying to be linear is greedy and is wrong in this instance. So this is our algorithm. No time to talk about it right now, but we can talk about it together. I can walk you through the stages at the poster. And the take-home message is we have an n square root of n algorithm, not an n squared algorithm, for maximum matching in an interval by graph. So the conclusion is evaluating SED is non-trivial or less trivial than most of us think, and solving it in sub-quadratic time requires an algorithm like the one we presented. This might seem like an odd thing I'm presenting. This algorithm runs at DCASE Challenge since 2020 in complete secrecy, but so I guess this year is a coming out of this algorithm. And so far, no complaints received. So we've done some speech benchmarks on BirdVox Full Night, a data set where we have 10K events and more than that, and there's absolutely no problem. It runs blazing fast. We have a complexity analysis, and once again, many thanks if you've programmed, if you've written software for evaluating, you know how tedious and technical this can be, so many thanks to you. Bye-bye.
Hello, my name is Maarten Meire and I'm a PhD student at KU Leuven, and today I will talk about my work on active learning in sound-based bearing fault detection. Well, I am working in smart maintenance or machine condition monitoring or whatever you want to call it. And what is the goal that we want to do? We want to detect faults in an unseen bearing. So we have a set of bearings and then a separate one, and we want to see how well it works on that separate one. But now the problem that, well, every data system has is you have collected a large amount of data, but now you have to start annotating it, and it's expensive, it's tedious, nobody really likes it. So can we reduce this, well, cost or amount of annotations that we need to do by using active learning methods? And then, well, what active learning method does actually perform the best, because there are a few of them. So how do we do this? We use a couple of sampling methods. So we have a classifier model that outputs some probabilities per class. We say, okay, we calculate a certain uncertainty metric. In our case, we used simple entropy, which is quite commonly used. Next to that, we use a distance similarity metric. In our case, it's semi-supervised detection of outliers. There is a paper about it. There's also a big formula on it. If you want to know more about that, I'll explain it at the poster. And then we create a ranking based on either only the uncertainty or a combination of both. And if you visualize it on the graph on the right, you see different colors. Basically, if you get a point in the top right, that it should be the most interesting point to actually label. Then we got some results. We see our uncertainty method increases quite rapidly. The hybrid method, not so much, which is not ideal, of course, but sadly it happens. But I guess the most interesting thing that we found is that if we look at what points are actually being asked labels for, they lie a lot around the point where a bearing actually fails, which was, well, quite an interesting find in our opinion. So if you want to talk about it more, please come to my poster.
Hi. This is my first time to present something, so quite nervous. Maybe our model can talk well better than me, so I guess so. My name is Jaewon Kim from Hanyang University. You can call me Jay, of course, if you want to call me. So we participated in the test 6A for audio captioning, and we thought the audio captioning metric originated from the video captioning. So sometimes the actual caption quality and the SPIDR evaluation metric had a disparity. So, for example, we did some reinforcement learning for one model, and actually you can see the SPIDR score was increased, but the actual caption quality was not exact, but and incomplete sentences and similar phrases were repeated. So thanks to DCASE, they introduced the new SPIDR FL score. And to manage this, we mainly did two techniques for synonym substitution and selecting the ensembles for the new model we couldn't just draw away for the reinforcement learned model, because it's actually a powerful technique to increase the performance. So as we did our technique, so the models had a higher performance for SPIDR if we did the reinforcement learning. Bottom three models were trained with the reinforcement learning, and the top four models were not, while SPIDR FL score is higher than which have done the reinforcement learning. But the thing is, if we only choose the ensemble for the higher scores for the Spider FL, like Ensemble 1 model is the four models of the non-reinforcement learning, and Spider FL score is similar to the highest one. But if you add just one reinforcement learning model, then both Spider R and the Spider FL score will increase. We add the reinforcement learning model as a regularization, and the actual caption quality was a much better, much exact, and complete the sentences and non-similar phrases. So I guess that's all. So please come to my poster and call me Jay. Thank you.
Hi, hello everyone. I'm here to present the paper called Automatic Detection of Co-Vocalizations using Convolutional Neural Networks. This work was developed by both universities, researchers from the University La Salle Campus Barcelona and AWEC Advisors. AWEC Advisors are a company of veterinarians that want to improve the animal welfare. So the context of this work is the CoTalk Pro project. In this project, what we want to do is to develop a sensor that can detect the co-vocalizations to give us data about their status, and this way know if they are okay or not. And do all of this avoiding physical manipulation of animals, so we try to be not invasive, just by putting an ambient sensor. Specifically, we want to monitor 3 particular periods on their lives. First of all, when they are born, during the first weeks of life, they can easily get sick. What we want to do is the early detection of sickness, so if they get a virus or something, they don't spread it to the rest of the yard. Then also during the dry-off periods, that is when the farmers stop milking the cows, they may experience some pain or discomfort, and this can be mitigated through changes on the food, so we want to detect if they are okay or not. And finally, during calving, we want to detect if the farmer assistance is required or not. So for this project, we have collected data into different farms, one in Girona, the other one in Valencia. And what we want to see is if deploying or developing a model with data from one farm can be used then in another farm to see if the model is generalizing. For this, what we have done is, after annotating our data, in this case, we're annotating both vocalization and coughs, we have split them in 3 training sets, one containing data from Girona, one from Valencia, and the third one is the aggregation of the other 2 farms. And in the test set, we only use data from Valencia. For the classification, we have used a mobile net architecture that uses the spectrograms as inputs. And we have seen, we can discuss more in detail the results during the poster, but we have seen that having data from the same farm in which you are evaluating is beneficial, but is not strictly necessary. We can achieve more or less similar results. Actually, we have a difference of 9% in F1 score, which is not that bad. Also, in the poster, we will discuss some post-processing techniques that we have used using different overlapping windows to improve the classification. Thank you very much.
So the next presentation is a video format, so let's hope it works.
Hello everyone, today I'll be presenting this paper P549, which is the Exploring the Multitask Learning with Weighted Soft Label Loss for Sound Level Detection using Soft Labels. This paper is being presented by Tanmay Khandelwal and Rohan Kumar Das at the DCASE 2023 workshop by Forte Media Singapore. We start with a brief introduction to sound event detection. Now, the sound event detection has the main objective to autonomously identify and extract meaningful information. This is done by extracting the different classes and marking their onset and offset when given an audio clip. This task actually faces significant challenge due to the absence of label training data, which is usually associated with high annotation cost due to factors like the judgment of the annotator. Now, in this work, we actually delve into the potential benefits of using soft label training data instead of strongly labeled data. Now, soft labels, as we know, is usually associated with a confidence score, which captures the uncertainty and the variability inherent in the sound events. Thus, this approach enables a more refined analysis in the decision-making process of the SED. Now, we introduce our method of defining it. Now, audio scenes that we see are usually associated and are interesting to understand any sound event. They provide the contextual information for sound perception. Now, our goal in this paper is to use these acoustic scenes to actually improve the SED methods. Now, for this, we introduce two additional tasks. One is acoustic scene classification. For every event, we try to classify the acoustic scene involved in. The second is acoustic event classification for the factor whether it's indoor or outdoor. Now, we combine these two tasks with the main task of SED as we see on the right-hand side. So once we have the output, we split it into three parts, and we have an individual GRU for all of these. We have the SED, the ASC, and AEC. Then we combine the loss for joint training. As we see, the LMTL is given by alpha times LSED plus beta times LSCS plus gamma times LAEC. Additionally, we also propose a weighted soft label loss, which allows the model to focus more accurately in predicting the instances with high probability while considering uncertainty associated with softer labels. Now, the outcome of this we see is the table on the one, we show how we use pans with 6 blocks and different feature extraction methods. We see that the pans with 4 blocks and MFCC performs the best, with improving the score of F1 around 48.2. We also show that using MFCC with the weighted loss function improves the score from 48.2 to 48.9. Further, after adding the branches like SCD plus ASC, we see it's at 49.2. With AEC, it decreases. But when we add in the 3 branches, it finally increases to 49.3. So we see that we are able to increase and achieve a remarkable 14.9 increase in the macro F1 score, which is usually optimized with thresholds per class, showing the effectiveness of the proposed system. Thank you.
Hello, I am Manjunath Mulimani. Today I am going to present our work, Incremental Learning of Acoustic Scenes and Sound Events. In this work, we are proposing a method for incremental learning of 2 distinct tasks. One is acoustic scene classification and another one is the audio tagging. The first model initially learns to classify the acoustic scene classification, and then in the incremental time step, the classifier of the model is extended to learn the sound event classes of the new task. The major motivation for this work is to simulate the scenario of the new information becoming available at the later time. For example, in this case, the model first learns the acoustic scene classification task, and in the later stages, annotator may come up with the more detailed information about the same audio material, for example, the sounds present in the acoustic scene. So in that situation, no need to retrain the model on the joint label of the previous acoustic scenes and the sound event classes. So this is the proposed method of our work. In this case, first we train the model using categorical cross entropy on the for the acoustic scene classification in the initial time step. In the incremental time step, first we train the model using binary cross entropy on the logits of the sound event classes, and also we preserve the knowledge of the previous acoustic scene classes using the knowledge distillation. So the output of the model in the incremental time step, it is the combination of 2 logits, the new logits for sound events and the old logits for the previous acoustic scenes. So this is the sum of the result on the incremental ASCAT. The last line represents the incremental ASCAT with knowledge distillation. So initially the model gives the 94% of accuracy on the acoustic scene classification task, and in the incremental time step, it achieves the 54.4% on the F1 score on the audio tagging task, and the performance on the previous acoustic scene classification, it is reduced to 88.9%. This is also called as the catastrophic forgetting. So but still the performance of this incremental ASCAT is better than the joint ASCAT system, which learns both acoustic scene classification task and audio tagging at the same time. So we presented two scenarios in this work. One is ASCAT and another one is the ASC-ASCAT. ASCAT uses the same audio recording but different labels for the two tasks. But in case of ASC-ASC, it is the model first initially learn the acoustic scene classification. In the incremental time step, it again learn the new acoustic scene classification, but it does not have access to the previous task data, both audio recordings and the labels. It is a clearly imbalanced situation. So there is no data of the previous task, and we have the only data of the current task, so that it encourages the model biased towards the new task and it completely forgets the old task. And how to avoid this and more about the result I will discuss in my poster presentation. And in this work, we significantly reduce the catastrophic forgetting by independently learning the new sound event classes without significantly forgetting the old acoustic scene classes using knowledge distillation. So thank you very much.
Hello everybody, I'm Tobias Marukuti, a Bachelor AI student at Johannes Kepler University Linz in Austria, and I'm working at the Institute of Computational Perception. Today I want to introduce you to our workshop paper, Creating a Good Teacher for Knowledge Distillation in Acoustic Scene Classification. So the task of acoustic scene classification is, as you probably know, to classify audio clips into distinct acoustic scenes, and these audio clips can stem from many different recording devices. Additionally, the task 1 of the challenge, of the DCASE challenge, has low complexity constraints, and to improve our low complexity model, we use knowledge distillation. Knowledge distillation is well researched, but there is a lack in starting which teacher attributes are beneficial for the student. So we use 3 different architectures. The first one is CP Mobile, short CPM, which is a receptive field regularized CNN, specifically designed for acoustic scene classification. The second one is CP ResNet, also a receptive field regularized CNN, which has been very successful in previous editions of the DCASE challenge. The third model is PAST, which is a spectrogram audio transformer pre-trained on audio set. For all of our experiments, our student is a CP Mobile model. So further, we experiment with device generalization methods. Frequency mixtel, short FMS, mixes frequency statistics of samples, and device impulse response augmentation, short DIR, convolves samples with device impulse responses to increase the recording device variety in the training phase. Further, we experiment with the combination of DIR and FMS, noted as DIR-FMS. So using this visualization, I can best describe what our paper is about. We have on the left side the teacher ensemble and on the right side the CP Mobile student. When we get the predictions of both, we can calculate our loss, which consists of the true label loss and the soft label loss. And when we evaluate our student on the validation set, we want to maximize the performance only by changing the teacher ensemble. So we ask ourselves questions like which models should we include to the ensemble, which complexity should they have, and which device generalization methods should be applied to obtain the teacher ensemble which results in the best student performance. So our key takeaways are that smaller CNNs can be better teachers even though they perform worse. Teachers trained with DFMS are superior to other teachers. The best teacher ensembles consist of CPR and past models and no CPM models, which suggests that CPM students learn better from other architectures. And finally, DFMS and FMS teachers are complementary. Thank you for your attention, and for more information, see you at the poster.
Hi, I am Hyun-Nam from Human Machine Interaction Laboratory of Korea Advanced Institute of Science and Technology. And I am going to present about the paper titled Frequency and Channel Attention for Computationally Efficient Sound Event Detection. So, frequency dynamic convolution has shown state-of-the-art performance in SED, that it is applied in many participants of the DCASE task 4, including the winners. However, it is computationally inefficient because it adds 150% more trainable parameters, and also it increased training time by 72%. So, if we want to apply sound event detection for practical use, then we need the sound event detection methods. Those are computationally more efficient also, and at the same time as competent as the current state-of-the-art method. So for this work, the approach is that we want to lighten the sound event detection models by addressing frequency and channel dimensions, which are shown to be effective on sound event detection. So we do that by using squeeze and excitation-based methods, which are light yet powerful. So these are the methods we experiment on this work. I think you should know squeeze and excitation, which reweights the channel dimension of the convolution output to reweight the channel dimension for the better feature extraction. Also, there is frequency-wise squeeze excitation, which reweights instead of channel dimension, it reweights frequency dimension. Also, we use time frame frequency-wise squeeze excitation, which reweights frequency dimension of each time frame. And lastly, we experiment on C2D attention, which reweights both channel and frequency dimension at the same time using 2D convolution-based attention. Also, we experiment using mixing the channel dimension and frequency dimension squeeze excitations. So these are the main results. So, the joint application of squeeze excitation and time frame frequency-wise squeeze excitation adds only 2.7% trainable parameters, and also it only adds training time by 15%, but its PSDS1 reaches almost 99% of frequency dynamic convolution performance. Also, we performed class-wise analysis with box plots, and it shows that frequency dynamic convolution, squeeze excitation, and squeeze excitation with time frame frequency-wise squeeze excitation, and C2D attention. These modules are better on non-stationary sound events such as alarm bell ringing, cat, dish, dog, and speech. And opposed to that, frequency-wise squeeze excitation and also time frame frequency-wise squeeze excitation performs better on quasi-stationary sound events such as electric shaver or toothbrush, frying, and vacuum cleaner. Yeah, thank you for listening, and let's discuss more on the poster.
So hello, my name is Noboru Hada. I would like to introduce toy add-ons to newly recorded data set and also the benchmark results of the fast shot anomalous sound detection baseline. So mainly there are two things. So introduction newly recorded data set, that is one thing. Another thing is benchmark results of the fast shot baseline. So, and also that is examining how it works to the old data sets from 2020 to this year, 2023. And so this one is a general program description with an anomaly detection task. So imagine you are asked to monitor some very expensive machine in the manufacture. And in that case, there are no broken data because it's very, very expensive. No one wants to try to destroy that one. So only the normal data sample is available. So this is kind of semi-supervised anomaly detection tasks that have only normal samples are available for training. So this is a setting. And so we organize some basic tasks as unsupervised detection of anomaly sounds for machine condition monitoring started in 2020. And next year, we explore it to domain shift conditions. And then yet next year, we also explore it to domain generalization tasks. So this is the previous years, but there are some difficulty or something wrong on the task settings because some proponent of systems are assuming that for their system, development data set can be used as a hyper tuning, but which means proponents are using the ground truth data to optimize the hyperparameters. But that is twisted settings because our motivation is training the system without having any anomaly data. So this is something distorting the setting at all. So, and yet another approach, it's very successful, but it's not applicable, is regarding some different instance of machines in the machine type is regarding it as applying the classifier and regarding it as pseudo anomaly samples. So in this setting, proponent can apply the classifier based on classifying the data sets, normal data sets. But however, requiring this training data set is not applicable to our actual application scenarios in the industry. So we set the first shot anomaly detection task. So no use of data from different machine instances are allowed, and no hyperparameter tuning shall be applied for dedicated machine type, and no tool ensemble applied for dedicated machine type. So this is a setting. So these are the kind of data newly recorded. So I hope you can. So this is a drone. So we intentionally make damage on like cutting the propellers or putting some offset weight on somewhere. So something like that. And so toy drone, toy train, and some other, like a toy train is like this. So recording conducted with using microphone, so it's a moving target. And also here is a vacuum. It's working? Should be. Okay. So conditions will be changed by replacing some carpet or wooden floor, and some bag is full, or remove that. So forgot to filters. So those are the kind of things we created. And so there are several information about how baseline software, baseline system should look like. But anyway, just come to.
thanks. So this is the last presentation of the last oral poster presentation session of DCASE 23. You all learn now that making data sets is a lot of fun. So you know what you have to do. And yes, also thanks all the authors for keeping the presentations in time.